Bismillahirrahmanirrahim. Assalamu alaikum, dear students. As you all asked me about the revision of our lecture regarding linear transformation, so today I am going to discuss about the linear transformation, the criteria of define how we define a linear transformation and how we check that if a particular transformation is linear or not linear. So first of all, a quick recap of the definition. A transformation is called a linear transformation if it is between the two vector spaces V and U. So a linear transformation is a mapping between two vector spaces V and U, and it is called linear if it satisfies the two conditions. Now these two conditions are written here, and these conditions are called are categorized as, I can say that the first condition is categorized as the linear transformation preserves vector addition. And the second property is characterized as it also preserves scalar multiplication. Now, what does it mean by that a transformation is preserving a linear or vector addition or not? So for this, I am explaining the fact like this, that suppose we have two spaces, the space V and the space U. So we have two spaces here, and we have two vectors, let's say V and W in the space V, and T is a transformation from V into U. And the image of V under T is TV, and the image of W under T is TW. Now suppose we are adding these two vectors in this space. So the addition is under the rule of how we define the vector addition in this space V. Now, if T is a linear transformation, then T transforms this sum as, that is, the image of this sum is the sum of these images. So again, the sum here is, since we are in this space U, so this sum is characterized as the sum defined as the vector addition defined in the space U. So this property, the preservation of vector addition, can also be written as the image of sum is equals to sum of images. So it doesn't make any difference whether we first add the vectors in the space V and then transform the sum, or we first transform the two vectors individually, V and W, and then adding them in the space U. So this is the first property of linear transformation. Now the second property is about the preservation of scalar multiplication. Now for scalar multiplication, we can see again that we have the two spaces V and U, and here we have a vector, and here we have image of this vector under the mapping T, and here we have a scalar times a vector. So K is a scalar, and we scaled this vector V with this scalar, and we transform this scaled vector under the transformation T, then the answer would be K times the scaled version of the image of V. So the transformation is linear if it doesn't make any difference if we first scale the vector and then transform, or we first transform the vector and then scaled it. So these are the two important properties that need to be satisfied for proving the transformation is a linear transformation. So what is the difference between linear transformation and linear operator? Basically, a linear operator is a linear transformation that is a self-map. It means that if we have a transformation or a function that is linear in nature and it transforms a space V into the space U, then we say that this is a transformation. And if we have a mapping that is a self-map from V to V, it is also linear, then it is a transformation also, but in addition to that, it is basically an operator. So a transformation becomes operator when it transforms the space onto the same space. So for example, the space of continuous functions, if we define the differential operator, then differential operator is a linear operator. As you know that if derivative of sum of two vector is the sum of derivatives of these two vectors. We have seen such properties in our calculus course. So this is a linear operator. Similarly, the integral operator is also a linear operator, and in the next few slides we will also see some examples of linear transformation and some examples of linear operator. Many times we call them the operators, and many times we call them as linear transformation. So there must not be any confusion between these terms. So as I told you before that a linear transformation preserves vector addition, it preserves the scalar multiplication, and it takes zero vector of the space V to the zero vector of space U. So now we will do some examples. The first example is the example of translation mapping. So the translation mapping can be defined as if we have the space R2 and some vector X and Y, or we can say that this point XY. After this translation, suppose this is 1 unit and this is 2 unit, then this point will be X plus 1 and Y plus 2. So this point translates into this points. So what happened to this vector, this point 0, 0 of the space R2? So if we see the image of 0 vector of R2, then it becomes 1 and 2, which is not equal to 0, 0. And since G cannot transform the 0 of R2 onto the 0 of R2, so this is not a linear operator. Translation is not a linear transformation. Transformation, or since it is from R2 to R2, so it is basically an operator. So it is an operator, but it is not a linear operator in this case. So next example is about the projection mapping. So the projection mapping can be defined as this is R3 space X, Y, and Z. Suppose we have a point in a space P, X, Y, Z, and this is its Z component, this is its Y component, and if we take the perpendicular projection here, then this is its X component. So we can see that this is point is the image of P under the mapping T. So this point is the projection of this point onto the XY plane. So this mapping we can prove very easily that this preserves vector addition, it also preserves scalar multiplication, and it also maps zero vector onto the zero vector. So the projection mapping is a linear operator. So the projection is linear operator, and also it is a transformation. So if it is written that projection is a linear transformation, then it is not wrong, because an operator is also a transformation. So the above two properties that we have discussed about the preservation of vector addition and of scalar multiplication can completely characterized by this condition. The only condition that covers both the factors of preservation of vector addition and scalar multiplication. Again, here we are adding vectors before transforming, so the addition is in the space V, and this addition is after the transformation, so this addition is under the space U. So now if we need to show that a transformation is linear, then what actually we need to show? So actually we need to either we need to show two conditions. The two condition is TV plus W is equals to TV plus TW, where VW belongs to V if T is a transformation from V to U. And the second one is T times KV is equals to K times T of V, where K is a scalar and V is a vector. So these are the two conditions, or simply we need to show that T of AV plus BW is equals to A times TV plus B times TW, where A, B are scalars and VW are vectors. So we need to show either these two properties or we need to show this property alone. So this is an example of how we show that a space is a linear, the transformation is a linear transformation. So here we are transforming R3 onto R2 with under the transformation T. So I am here doing this example by taking the two conditions uh, alone. That is, first I discuss about the preservation of addition, and then I discuss about the preservation of scalar multiplication. Now for this, let V and V1 is a vector in R3, and V2 is also a vector in R3, where V1 can be taken as X1, Y1, and Z1, and V2 can be taken as X2, Y2, Z2, and we see that V1 plus V2 is equals to X1 plus X2, Y1 plus Y2, Z1 plus Z2. Why I added it like this? Because the operation of addition is not defined here. So in obvious situation, I think, or it is by common sense, I considered the addition to be the addition defined in R3. That is the vector addition component wise. Now here, if we take the image of this sum V1 plus V2 by using this definition of T, applying on the sum would be x1 plus x2 plus 2y1 plus 2y2 minus 3z1 minus 3z2, and the next component is 4x1 plus 4x2 minus 5y1 minus 5y2 plus 6z1 plus 6z2. And after breaking this component, these two component, by using the properties of vector addition, we can write it as x1 plus 2y1 minus 3z1 4x1 minus 5y1 plus 6z1. This is the first one, and the second one is x2 plus 2y2 minus 3z2 4x2 minus 5y2 plus 6z2, and this is t of v1 plus t of v2. And here you can see that since this is a two-dimensional vector, so this sum is the sum in the space R2, and the sum is defined component wise, the standard vector addition defined in R2. So in this manner, I showed here that the mapping T preserves vector addition. Similarly, we can do this for scalar multiplication. Like let K be any scalar in R and V be the vector X, Y, Z. Then we show that K times V is equals to Kx, Ky, and Kz, and T of Kv is equals to K times X plus 2K times Y minus 3K times Z 4k times x minus 5k times y plus 6k times z. And taking k as a common, we left with x plus 2y minus 3z, 4x minus 5y plus 6z, and this is equals to k times t of v. So this mapping also preserves vector scalar multiplication, and hence the mapping satisfies both the conditions, so it is a linear transformation. So it is obvious if a mapping satisfies the two conditions, then it is certainly satisfied the condition of mapping zero vector onto the zero vector. So by doing this example with vector addition and scalar multiplication, we can do it like by combining the two conditions, as let we take a, b the scalars and v1 v2 with the two vectors in R3, and we would have proved this condition like this. We first add these two vectors and then take the image, and we take the images and then add, and we can show this very easily that these two sums are equal. So there are the two ways of showing a transformation is a linear transformation. Now what we have to do if we have to show that the transformation is not linear, we just need one such example that counters either or that counters either the vector addition that is, it does not preserve vector addition, or it does not preserve scalar multiplication, or it does not map V 0 of v onto 0 of u. So if we can find one such counterexample that violates either condition 1 or condition 2 or condition 3 or any of one condition, if the example violates any of one condition, then the transformation would no more the linear transformation. So we can see by taking the example, for example, in this first one, this mapping T1 is not linear because it does not preserve vector addition. The vector addition is not preserved. So you can show this easily by taking any example. For example, let v1 is equals to any vector in 2 dimension and v2 be any vector in 2 dimension, and then we take v1 plus v2, this is equals to 4, 6, and if we take the image of this sum, then this is 4 6 are 24, 4, and if we take the images of v1, it is 2 1, t of v2 is 12 and 3. So t of v1 plus t of v2 is equals to 14, 4. And if we compare these two, then these are not equal. So it does not preserve vector addition and hence it is not linear. So in the second example, you can see that this mapping T2 is not linear because it does not preserve, it is not linear because it does not map 0 of R2 onto 0 of R3. Because if T2 of 0, 0 is equals to 2, comma 0, comma 0, which is not equal to 0 of R3. So this violates the third condition. Similarly, in the third example, we can show that this mapping is not linear because here scalar multiplication is not preserved. For example, let k is equals to -2 and v be any vector, let's say 1 2 3 belongs to R3, and you can see that k times v is equals to -2, -4, -6, and the image of k under 3 t3 is equals to 2 and -4 -6, which is equals to 2 and 10. On the other hand, if we take the image of v, then it is 1 and 5, and if we take the k times image of v, then it is -2 times 1 5, which is equals to -2 -10. And if we compare these two, then again these two are not equal, and so we can say that T3 is not a linear transformation. So that's all in today's lecture. So I make it brief because of the time, that you can absorb the concept easily, And in today's lecture, I discussed about the linear transformation and its some examples. Please give me the feedback about the lecture, and you can post comments into the comment section. Thank you very much for your attention.